Hello, it's Scott Manley here. On Monday morning, less than a day after SpaceX had flown IFT-5, it was going to carry one of the most important missions in its history. On top of a dedicated Falcon Heavy, Europa Clipper was going to fly. Moreover, this spacecraft was so large, so ambitious that they were going to have to use the entire capability of the Falcon Heavy with no stage reuse. As I like to say, faced with the tyranny of the rocket equation, they made the decision to sacrifice all three cores of a Falcon Heavy to appease the Dark Lord of Delta V. Now, to be clear, NASA has thrown spacecraft away from Earth at higher velocities. Parker Solar Probe took an entire Delta IV plus a kick stage. New Horizons went off to Jupiter in record time, and it actually holds the record. But both of these spacecraft are really small. Europa Clipper is an absolute monster. At this moment, when Falcon Heavy let it go, it massed over 6 tons. The only space probes that are heavier are China's Chang'e 5 and 6, but they only went to the moon. This will eventually arrive at Jupiter in 2030, and it could have got there faster because originally it was supposed to use the SLS as launch vehicle. And that could in theory have thrown it straight to Jupiter without any gravity assist or anything. And that would have been great, it would have been hideously expensive, but it can be argued that having it as a possible payload for SLS helped it survive in Washington, at least long enough until they saw the sense in a vastly cheaper launch vehicle. Expending an entire Falcon Heavy allowed it to be delivered onto a hyperbolic escape trajectory from Earth with an excess energy, or C3, of about 40 kilometers squared per second squared. I know that sounds strange, but this is actually a measure of kinetic energy. When we talk about orbital mechanics and trajectories, we talk about C3 for escaping Earth, and it's effectively a measure of excess kinetic energy. The reason we use this is because when you have a spacecraft on a hyperbolic escape trajectory, as it climbs up out the gravity well, its velocity is slowing down, its kinetic energy is dropping. But what isn't changing is the amount of excess kinetic energy it has over the amount required to escape gravity. So when it reaches infinity, it will have this amount of excess energy. And you can basically take the square root of this, and that gives you the velocity. So yeah, they have a C3 of about 40. Take the square root of that, it's about 6.3. So when this reaches a hypothetical infinity, it will be moving at 6.3 kilometers per second. That's about 3 kilometers per second short of what's needed to go directly to Jupiter. So instead, SpaceX has thrown this space probe to Mars. Yes, Elon Musk really likes to talk about going to Mars, but they haven't actually sent any spacecraft. And Europa Clipper is just going to be flying by. Incidentally, the Hera mission, which was launched about a week before, it's also going to go straight to Mars for a gravity assist, but it's actually going to arrive later because, of course, it was launched at a lower velocity. So yeah, Europa Clipper, its first encounter is Mars. That will kick it out into a slightly further orbit, and from there it will begin to swing back in and eventually encounter the Earth. And it'll no doubt wave as it goes past, picks up some speed, and then it is on its way out to Jupiter. It basically will come out in front of the planet. Jupiter will actually catch up with the space probe, which will fall in towards it, and that's when it'll start encountering Jupiter's moons. Ganymede, of course, because it flies past Ganymede as part of its capture process. It gets a little gravity assist. It's using its engines to slow down. During its initial descent and capture into the Jovian system so it can start encountering Europa, it actually encounters Ganymede multiple times. Ganymede is the largest moon, making it one of the best to manage the spacecraft's velocity. And so I know what you're thinking. We've thrown away this massive rocket, we've done all this complicated orbital mechanics. What are we doing this for again? Well, as most of you have guessed from the name, it's going to the moon Europa, which is the second of the Galilean moons. So named because Galileo discovered them. He pointed a telescope at Jupiter and he saw that there were these stars next to it that would move around it in a plane. And through most of human history, they remained as dots of light that we didn't know very much about. Jupiter was big enough that people looking through telescopes would draw sketches showing the layers and the red spot. And then the invention of photography enabled them to cut out the middleman and convert those photons to an image that was more objective. But even the biggest telescope in the world could not provide any details on those Galilean moons. It would take Pioneer 10 to swing by and show us this smudged image, which is better than you can expect when you consider it didn't really have a camera, it had an imaging polarimeter. It wasn't until 1979 in the Voyager spacecraft that we began to really get an idea of what Europa was like. We saw images of a world which looked like it had a surface of ice, with cracks on it and areas that had moved around like tectonic plates. But as amazing as the Voyager missions were, they were just flypasts and they didn't stick around long enough to help us answer all the questions that were raised. But by the end of the 90s, we had Galileo on scene. And it spent years orbiting in the Jupiter system, taking photographs of everything. The only problem was that it had a problem with its antenna, so it had a really hard time downloading the copious quantities of scientific data it collected. But Galileo's imagery allowed us to estimate the age of the surface by looking at crater counts, and it showed that Europa was a really young surface, like probably less than 60 million years old. That means that it was continually resurfacing itself. Europa was also shown to be one of the least mountainous bodies in the solar system. It's actually very, very spherical, and its surface has a pretty high albedo. It reflects a lot of light. But it wasn't the images that were the big deal, it was the magnetometer readings. Every time Galileo flew close to Europa, its magnetometer showed an unusual kink in Jupiter's magnetic field. And this is believed to be because Europa has a subsurface ocean, a salty subsurface ocean that's able to conduct electricity, and therefore, as it moves through Jupiter's powerful magnetic field, it in turn produces its own magnetic field, which counteracts this. Now, reasonable modelling of this suggests that Europa's ocean is so deep that it actually has more water than Earth, despite the fact that its surface is so much smaller. And there is another critical piece of evidence. We've now seen plumes that are ejecting material from inside Europa. That is cryovolcanism. At this distance from the Sun, Europa should be a solid block of ice, but Jupiter's gravitational influence and interaction squeeze the planet and warm it up. And so we have another world in the solar system with a liquid ocean with energy that is being pumped into it to keep it liquid for long periods of time. And so given these conditions, it seems not unreasonable to ask, could you have some sort of life or at least precursors to life forming in these conditions? And so Europa Clipper is going to be on the scene with the latest in scientific instruments. In fact, it's actually going to have another spacecraft, the Jupiter Icy Moons Explorer from Europe, that's going to arrive around the same time. Although the European spacecraft isn't going to focus on Europa, it's going to focus on Ganymede and Callisto, for one very important reason. Jupiter has massive, intense radiation belts, just like the Earth's Van Allen belts, but way worse. These are the Van Allen belts that the conspiracy theorists are warning you about, the kind that could kill you in a matter of hours. And this radiation is absolutely powerful enough to slowly kill a space probe if it goes into the wrong region. The Juno spacecraft, for example, it was originally set up in an orbit that went over the poles and then inside the radiation belts to minimize its exposure to that. But even then, it's still slowly degrading as it's passing through these different belts. And so while there are some gaps close in, if you're careful like Juno, generally, the closer you are to Jupiter, the worse the radiation. So Io is absolutely a place that you do not want to be sending a spacecraft. Europa being the next one out, it has much harsher radiation environment compared to Ganymede or Callisto that are further out. And so there's two primary ways the spacecraft deals with this. The first is by having an orbit which doesn't spend all its time in the radiation belts. It's going to actually be on an eccentric orbit which swings out and then comes in just for a few hours to swing by Europa, get some science, and then send back into deep space where it can process it, send it back, and decide what to do next. And the other way is they have a radiation shielded vault. And I say radiation shielding, it's 1 centimeter of aluminium. It's not much, but it's more than a lot of spacecraft get. They put the most sensitive mission-critical components inside this, and they carefully had to, piece stuff together to make sure that it all fit. And of course, many of the scientific instruments, they were sensors. They couldn't be inside this radiation vault, so they just have to handle whatever Jupiter's magnetic field throws at the spacecraft. And perhaps the biggest component that is going to be affected by the radiation, which they can't do anything about, are the giant solar panels. Jupiter is about 5.2 AU from the Sun, which means that it gets about 3.5% of the sunlight that you would get at Earth. And that is why it needs these absolutely massive solar panels to soak up what little solar power there is to power its instruments. When the Galileo spacecraft went to Jupiter, it brought along a radioisotope thermoelectric generator. But improvements in solar cells and in efficient electronics means that it is absolutely viable to run spacecraft using solar panels in the dim sunlight out at Jupiter. You may remember that the Galileo spacecraft, which orbited at Jupiter, had two radioisotope thermoelectric generators. Those are the two sticking out on booms, the shorter booms, not the big long magnetometer. Between the two of these, the spacecraft had just under 600 watts of power at takeoff, and of course it had excess heat, which is used to keep the spacecraft alive. Incidentally, Galileo's kind of interesting as a spacecraft because they couldn't decide whether they wanted a spacecraft that spun or a spacecraft which was, attitude stabilized, and so they did both. They had a rotating section which had the magnetometer so it could sweep out different angles, and then they had the other instrument platform through a rotating bearing, and that would hold still and take pictures of things. Anyway, the heat in these generators was provided by plutonium-238, and it required a very specific reactor process to create this stuff. And in the 80s, they created a bunch of this stuff using the same facilities that are used to make nuclear weapons. But as a result of arms limitations treaties and the fact that they had a stockpile, they kind of stopped making it. And it was only in the last 10 years that they've actually restarted production of plutonium-238. And that's good because we're going to need a lot of it for the Dragonfly spacecraft, but that's going to Saturn underneath the clouds of Titan. Europa Clipper is going to be bathed in continuous, if weak, sunlight, and there is enough there that it can use very large solar panels to generate its power instead. But radiation at Jupiter is expected to significantly degrade these panels over time. Now, the other issue with being very far from the Sun is that it's very cold and the spacecraft needs to have its temperature maintained at a reasonable limit. So, of course, you have lots of multi-layer insulation expertly sewed into blankets. Yes, sewing is absolutely an engineering skill, but the blankets primarily just keep heat from moving in and out of the system. There's also a complex heat redistribution system inside the spacecraft. This will scavenge heat from the electrical, the avionics system, and pump it down to the propulsion system to make sure that is maintained. And when they're in the inner solar system, when they're doing all those gravity assists, they're getting too much heat from the sun, so they actually have a radiator system which can open up and reject heat into space. In fact, this thermal control system was somewhat over-designed. It would actually allow the spacecraft to go in as close as Venus, so it could have performed, flypasts if that was necessary. But the trajectory it flew was based on the launch window that it had, and ultimately that capability wasn't needed, but it's nice to have. So anyway, let's talk about the scientific instruments. Remember, Europa is the focus. We're really interested in what's going on underneath that ice surface. And one of the ways that we can look inside that ice surface is using the magnetic field, the way that it is tweaking the Jupiter's effects. So we have a magnetometer on there. And of course, it sticks out on the end of a very long boom that slowly deploys. They want to move this as far away from the spacecraft as possible to avoid affecting the readings. So this boom is about 9 meters long, 28 feet, and it has to deploy after takeoff in zero gravity. This is some great videos showing them actually testing the deployment mechanism back on Earth. You notice that they have all this hardware that's designed to support it and make it feel as if it's in zero gravity. And this moves the 3 Fluxgate magnetometer instruments a long way from the spacecraft, limiting the effects of the spacecraft's magnetic field and making it a little easier for the scientists to tease out that small signal from the Jovian system.
The other instrument designed to look at the magnetosphere is the Plasma Instrument for Magnetic Sounding, or PIMS, and there's actually two of these on the spacecraft in different locations. These are basically Faraday cups. If you don't know what a Faraday cup is, it essentially measures how much plasma is flowing in. And these Faraday cups, they can actually detect the direction somewhat. There's like different segments on the back that are, will provide different measurements of the flux. So plasma is extraordinarily important to understanding the magnetosphere around Jupiter, because if you've got jets of material coming off the moons, that's going to get ionized, it's going to get converted into a plasma and trapped in the Jovian magnetic field. So you want to measure that. And the spacecraft has 4 of these so it can detect flows from 4 different primary directions. Of course, the thing that will grab the attention of the general public are the cameras, and there's lots of them on there. So there's the basic Europa imaging system, and that's actually 2 different, a wide angle and a narrow angle camera. They're 8 megapixels, visible light, infrared, that kind of thing. Then there's a thermal emissions imaging system, right? E-THEMIS, and that's basically supposed to look for hot and cold spots on the icy surface of Europa. If you have a hot spot, it's a bit like a hot spot on the Earth where you've got a volcano, except this is a water, cryovolcano that is reaching closer to the surface. This can help to find active regions on the surface, which might provide newer material near the surface for analysis. And then we have the Mapping Image Spectrometer for Europa, or MICE. This is more or less a spectrometer which is going to work on the surface. It's going to map out large areas and look at the broad spectral properties. And that will let you detect things like ices, salts, different organic molecules, and map their distribution across the surface of the moon. And then we have the Europa ultraviolet spectrograph, which really isn't an imaging system. It's going to take highly detailed spectra, getting the emission and the absorption lines to let you analyze components of the atmosphere. This isn't actually going to be pointed at Europa. It'll be pointed at distant stars with a well understood spectra. And as the spacecraft moves near the planet, the light from that star will pass through the atmosphere and enable us to figure out what the atmosphere is made of. But more interestingly, if the spacecraft and the star are placed just right, it can pass through a plume from a geyser, and we could take a look at the detailed, molecular makeup of what is inside these plumes. But why just look when you can touch? You've come all this way. Wouldn't it be cool if the spacecraft could actually fly through one of these plumes? Now, it's not like, for those of you who have played the Elite Dangerous, where you can fly, drive over these things in your rover and have yourself kicked up into the air. No, these things are far too tenuous to worry about that. But these plumes are emitting material up high enough that the spacecraft could, in theory, fly through one of these. And if we're lucky enough for that to happen, there is an instrument on board called mass specs. And from that name, you can probably guess that it's a mass spectrometer, right? But because it's NASA, it has to be an acronym, right? So it's an acronym for Mass Spectrometer for Planetary Exploration. Okay. Anyway, look, it's an awesome instrument. It's your classic mass spectrometer. It's going to, zap any materials coming in, knock electrons off them, accelerate them through electric fields, twist them, turn them with magnetic fields, and depending upon how much they're bent, we can measure the mass of the ions that have been generated, and therefore know exactly which atoms are involved. And so if the spacecraft flies through a plume, it will be directly sampling the ocean underneath the ice of Europa. The other direct sampling system is the Surface Dust Analyzer, or SUDA. And this basically opens its mouth up wide, and as it flies through space, dust grains fly in, just like a whale going through the ocean and eating plankton. But when the dust particles come through, they hit the surface, it's sufficiently energetic that you create heat, you create ionization, and as the ions get pulled around, they can measure the timing of arrival to figure out, the mass to charge ratio on these particles. So they're basically measuring the chemical composition of dust particles. And the final scientific instrument is REASON, which is a radar sounding instrument, and it's attached to the solar panels, which is kind of interesting when you go to NASA's website that lays out the instruments, because the 3D model viewer for this instrument shows it just sort of floating disembodied in space. But yeah, this is obviously set out on these large solar panels. It spreads them out with large antenna, and it will transmit radio pulses, and they will be able to get radio signals back, and that will of course penetrate into Europa and give them some idea of sounding underneath the surface. It can use a range of radio frequencies, and it's expected that some of the high and very high frequency signals will penetrate up to 30 kilometers inside Europa, possibly below that ice sheet on its surface. And of course, as with almost every other spacecraft, there's the free gravity science that they're going to get just by monitoring the subtle changes to the spacecraft's velocity measured through the shifting of its radio frequency communication. And of course, that same Doppler shift effect is actually going to be very useful when you're, say, navigating through the solar system to get to the target. Over the next 6 years, yes, it's going to be flying by Mars and then the Earth and eventually onto Jupiter. Unlike Galileo, this spacecraft isn't going to be flying by asteroids in deep space to do science. I don't even know if they're going to be doing any science as they fly by Mars or Earth, but it seems like a good opportunity to test out some of the instruments. So ideally, the next 5 years or so are going to be relatively quiet. A couple of flypasts of planets without any real science going on, and instrumentation and systems that do exactly what they're told until they get to the vicinity of Jupiter. And then that's when the real excitement is going to start. That's where we are going to get a window into Europa. And, Europa is the target for this mission because it's arguably one of the best candidates for places for life to have formed independent of Earth. You see, there are other icy moons around the solar system which we believe have subsurface oceans at some level, but Europa is the innermost icy satellite in the Jupiter system, and the 4 major satellites in the Jupiter system all get squeezed by Jupiter's tidal effects as they go around their orbit and they go from perigove to apogee. And the closest moon in, Io, it's heated so much by this that it has, actual legitimate volcanoes. It is one of the most volcanically active planets in the solar system, moons. Europa is a bit further out. It still has energy being input into it, and enough probably to keep a large part of itself, liquid, and possibly even enough that you have things like, fumaroles, geological activity which is injecting heat into the ocean from below, possibly with black fuming chemical injections, right? So what I'm saying is there's a lot more energy coming into Europa. When you go out to Ganymede and Callisto, that energy drops off. And similarly, if you look at Enceladus around Saturn, it doesn't have nearly this level of thermal energy going on. And we know that ecosystems of all sorts have to be powered by an energy source. And most of the Earth, of course, is powered by photosynthesis on plants, but there are these small, deep ocean communities around fumaroles where you have energy coming in the form of chemical energy that is hot and being injected into the ocean at that point. So in the case of Europa, it's very unlikely that photosynthesis will be occurring because not only is it deep, distant solar system, but the liquid water is believed to be a long way below the surface, and the light just, is extinguished far too quickly to produce energy, to provide any light energy to the ocean underneath the moon. But maybe we have volcanic energy coming up and feeding the, whatever's there from below. It's certainly probably injecting active chemicals. And, you need this sort of active chemistry, we believe, to have any kind of abiogenesis. Furthermore, because Europa is in this intense radiation zone, it's constantly being bombarded on the surface, and there's all sorts of radiation-induced chemical reactions that happen there. And as the surface cycles over during time, that material could actually be injected into the subsurface ocean and be another source of chemical complexity. But before you get too excited, I really need to set some expectations here. Yes, this is the most advanced spacecraft ever sent this far into space. Yes, Europa is one of the places where we should be looking for potential life beyond Earth. But this spacecraft, for all its capabilities, its primary mission is to find out more about Europa. And that means more than potential indications that there's something alive there. In fact, it's almost certainly not going to be able to prove that life exists, at least to the satisfaction of scientists. It may find that some chemical processes have imbalances that are not consistent with passive chemical processes. That's science speak for saying that something alive is doing something weird to the chemistry. That's probably not going to happen. It's probably going to find out a whole bunch of other equally fascinating stuff about the moon and about the Jovian system, especially working in concert with the European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer. And between them, they will almost certainly raise questions which cannot be answered with the instrumentation sent. And maybe one day we will send something even more capable that may one day confirm or give our answer one way or another. If you want to watch something exciting about the discovery of life on Europa, there's actually a movie from the 80s. It's called 2010. It's actually a sequel to 2001. And I absolutely love it and highly recommend it. And sure, there's going to be a lot of film nerds out there that say, how could you possibly recommend the sequel to the greatest space movie ever, 2001? You know what? The biggest problem with 2010 is that it's a sequel to 2001 and therefore was forever doomed to live within the shadow of its great predecessor. Regardless, I'm sure some of you will find the time in the next 6 years or so before Europa Clipper actually gets to Jupiter and starts doing the real science. I'm Scott Manley. Fly safe.